So, good afternoon, everyone. For the last session, in earlier session, we discussed the storage rights. One of the problems. Like if you look at the storage, there are different uh, facets to look the particular problem from the energy storage or battery storage point of view. One is uh, from the electric vehicle point of view, and that vehicle is basically uh, try to optimize its range over the different constraints, which can be availability of the different charging stations, and how much distance it can travel, what can be the different prices, like the at the time of charging. Okay, and what is its current SOC, and all these constraints can be there. And another is basically from charging station point of view, that how much power it can acquire. Okay, and so those kind of constraints are there. Then we looked at storage from the large storage point of view, that if large storage is there, it will be it may be underutilized. In that case, he can basically sell certain rights to the different participants who wants to have the balancing support, which can be provided from the energy storage, but do not want to invest that very high capital. So from those point of view, we discussed that charging rights can also be procured. And in the charging rights problem, we have seen that how the storage can balance out the renewable production, how it can be helpful for the arbitrager, like how we can make money out of the energy storage. And so those kind of problems we have discussed so far. Here we were discussing that this entire problem is like we have to solve it all together, because it is one problem where one storage is being basically acquired by different players, and they have some common constraints which is identical for, so it's not common, it is identical for each player. Then we have some arbitrators, their objective, some producers objective, then some storage owners objective. And in storage owners objective, we can see that a storage owner, uh, how much rights he can provide is restricted by the maximum capacity of charging, discharging, and energy, which are like physical limitations over energy storage. So if I don't have these constraints, then all of these four problems or three problems are completely separate, and we can solve them separately. But as this constraint limits the how much rights one person can have, and so these all problems has to be solved together, and generally these constraints are called complicating constraints. So let's see how the problems can be uh, defined. So I will give you very fundamental a very basic example of a problem. Let's say a linear problem we are looking at. So, um, let's say minimization or maximization of a certain objective, and we have some a1 x1 plus a2 x2, and then let's say plus b1 y1 plus b2 y3, and then plus c1 z1 plus C2 Z2 plus C3 Z3. Okay. So these are the let's say the objective where x1, x2, y1, y2, and sorry, this is y2, z1, z2, z3 are variable, and subject to, let's say, some constants are there. So the constants are some coefficient, let's say a11 x1 plus a12 x2, and then a21 x1 plus a22 x2, and that is let's say either equality constraint or inequality constraint we can define. So let's say E1 and E2 equality constraints are there. Then some another constraint is, let's say, B11 Y1 plus B12 ABCDEF1. Okay, and then we have some C11 Z1 plus C12 Z2 plus C13 Z3, and let's say some G1 constraint is there. Then let's keep another constant which is like D11 X1 plus D12 X2 plus D13 Y1 plus D14 Y2 plus D15 Z1 and Z2 and Z3. Okay, so these are the constants, and let's say H1. So if you look at these problem, then I'm define like all of the X, Y, and Z are greater than equals to 0. Okay, so this is a classical minimization problem is defined. Now, if you look at this problem, it has certain unique features. So overall, X is basically the number of variables we have is 2 plus 2 plus 3. So overall is 7 number of variables, and these variables have a specific condition that a set of variables are clubbed, are basically constrained by these two equations. Uh, then another variables are constrained by, let's say, one equation, and this can be constrained by one or two equation, or let's say in this particular case one equation. This particular equation binds them together. Okay, here, like let's say if this D13 D14 is 0, we can say Y is separate, but still X2 or Z12 Z2 Z3 are bound together. So we just to keep it generalized, let's say this constant last one basically binds them together. If we don't have this particular constant, let's say if I don't have this one, the entire problem can be solved separately. It's basically minimization of we have a1 x1 plus a2 x2 and subject to some a11 x1 plus a12 x2 equals to um, e1 and then a21 x1 plus a22 x2 equals to e2. So like if we do not have this last constant, then I can simply solve this x1 x2 and these two constants can be like clubbed together, and we can solve it separately. Similarly, I can solve the another problem which is minimization of, let's say, b1 y1 plus b2 y2, and similarly minimization of c1 z1 plus c2 z2 plus c3 z3. Okay, and subject to the respective constant, and in just to keep it generalized, I can say that uh, y1 and y2 are set of feasible solution space. So these constants basically bounds the entire solution space. So whatever is the solution space bounded by the constant, so let's say this is defined by this particular equation. Here as well, I can replace this to keep it generalized, like x1 and x2 are set of some x. Okay, so all the constants which are only between x1 x2 can be defined that they create a solution space, and those constants are defined in generalized form with a single equation. Similarly, I can put here as well that z1 z2 z3 are basically a set of total space z. Okay, so I can solve this problem separately, and if it is a very large problem, solving them separately will give me some benefits, but still this constant is basically restricting it. So let's say by some means, if we can relax this one, relax this constraint, we can solve the above entire problem into three parts. Okay, so you can see from here that so this kind of constraint is called complicating constraints. Okay, so this is nothing but an example of. So we are actually looking at the like how we can distribute our optimization problem. So if we have one single optimization problem, how we can distribute it. So we are looking at the distributed optimization. Okay, so distributed optimization. This is the example of complicating constraint. Okay, so this constraint is basically creating the complication, or this constraint is providing a coupling between the different problems. If this constraint is not present, we can easily solve the entire problem separately. Okay, uh, just a second. Yeah, excuse me. So so yes, this constraint is basically a complicating constraint. So I can call it, this particular constraint is the complicating constraint. Okay, this particular constraint is complicating constraints, and if we can get rid of this particular constraint, we can easily solve this particular. Let's say another example of the problem. So we have to identify, let's say, another example. If I talk about, okay, so another example is like how we can solve a particular problem, and let's assume some minimization. Yes, so let's say minimization of a1 x1 plus a2 x2 plus, let's say, b1 y1 and plus c1 z1 plus c2 z2. Okay, let's keep it, and this is the objective function. Okay, and then if I put certain conditions, and that conditions can be like, let's say, a1 x1 plus a12 x2 is equals to e1, a21 x1 plus a22 x2 equals to e2. Okay, so let's say these are the constraints. Similarly, we can place a constraint between some b11 y1 should be equals to, let's say, f1, and then we can place c11 z1 plus. So there is a question: aren't they be combined? Uh, which constant we are talking about? Can you be more? Yes, you can
A1,
unmute yourself and ask, please.
sir, A11 X1 and A22
So,
X2
are
is
we talking about this particular formulation?
yes, sir. For the X1 X2 constants, they are linear and they can be added to make just a With
What will be the benefit of that?
both are equality constants now. So it is one is will be written.
Okay, let's okay, let me move this side. So if it is a two variable problem, generally we can solve it. Let's say so x1 is here and x2 is here, and let me have 5x1 minus 5x2 less than equals to 5. So what will be the line which it can represent? If I put x2 value equals to 0, x1 will be
One
1. So this is 1 comma 0, and if x1 is 0, x2 will be
minus
so 0 and minus 1. So this is the line we will obtain,
okay.
something like this. Okay, then if I put let's say 2x1 plus 5x2 equals to 3, let's say 6 and 10, assume 10. So if x1 is 0, then x2 will be 2. So somewhat here, let's say x1 is 0 and 2. And then if x2 is 0, it will be 5. So somewhat here. Okay, so let's say it is 5 and 0, and the line will be something like this. So the optimal solution will come here. If I add them up, I will end up with like 7x1 and then plus 0 equals to 15. Okay, so so far they are equality constants. Maybe if instead of equality they can be have less than equals to or greater than equals to conditions, then they creates a solution space. So these are basically constants. uh, they have certain significance. Okay, so maybe a few of them are equality, few of them are inequality, and so far I have considered equality constant, but it's not advised to like add the constants, and it is not advised. Like otherwise what you can do is you can create as many constant as you want, but they won't make any difference.
And
Okay,
it has only feasible point.
sorry.
It has
Yeah,
only one feasible point.
because we had a equality constant, that's why it has only one feasible point, and that will be the only solution for x1 x2. But if instead of equality, let's say if it is less than equals to conditions, then we have many number of points,
Conditions. Yes, sir.
right? So that create a solution space. So okay, you are also right. So I can put instead of this, I can put less than equals to condition. So that is also fine, I think, right?
Yes, sir.
Yeah. So they are basically, let's say, less than equals to. Then we cannot merge them. They will create a solution space, and that solution space is defined like this. That these constants defined as solution space, and some x1 x2 will be there in this particular solution space for which we are trying to solve this particular problem, right? So we can define it like this, like in mathematically we can write it like this. So actually this means that you these constants are to be written here. Okay, so similarly we were writing that, like say c1 z1 c12 z12 is okay less than equals to or equals to whatever. So let's say some g1 and c12 z1, or let's keep only one constant here. Okay, sorry. So far, if you look at this particular problem as well, it is same. Nonetheless, both are same. But if I add another variable here, okay, one more variable, let's say that variable is plus some, let's say d1, and we have used x, y, z. Let's say put some m and variables, so m1, and let's say variable is, let's say p. Okay, So K1 P1, let's say K1 P1. So this is D1 P1 less than equals to E1 plus D2 P2 less than equals to E2 and plus D3 P1. So these are only P1 only. So let's say F1 plus D4 P1 less than equals to Z1. So if this is the structure of the problem, you can see that if P1 is fixed, if P1 is fixed, then let's say, so if P1 is fixed to a certain value, then this term is fixed and it will come here. This term is fixed, it will come here. This is also fixed, this is also fixed. And then we can easily decompose this problem into three parts. Correct? So I will put only one, and then you can write down like, x1 plus a2 x2. If p1 is fixed, then this entire term will also be fixed in objective function as well, and then subject to a11 x1 plus a12 x2 is less than equals to, let's say, e1 minus d1 p1 at a some certain fixed value. Similarly, a21 x1 plus a22 x2 and less than equals to e2 minus d2 p1 at a particular fixed value. So this is how I can divide this into one. Then you can write it down with the y, okay, and then you can divide it and write it down for the z as well. So we can still get three different problems from the same. We can solve them like, separately. So this is the decomposition we can perform. But the issue is this one variable p1 is basically creating a problem here. So this particular example is for this particular variable is called complicating variable. Okay, complicating variable. Okay, so if we can handle either these complicating constants or complicating variable, we can easily solve a particular optimization problem in distributed fashion. Okay, so now if I put everything like how we can what can be the application of this particular problem in our power system. So for that, let's discuss it. Let me share it again. Share and okay. So what are the different application of this particular problem? So let's discuss it. So what can be the distributed optimization for power system operation? Okay. So the very first is what is a different optimization problems? What are the different optimization problems available in our power system operation? So we know that economic dispatch is one problem, unit commitment is problem, optimal power flow. So these are like, different optimization problems. And if we look at the optimal power flow, we have learned that it is of a DC AC. It optimizes the power transfer and it constrains the considers the network constraints. And byproduct is nodal prices. Okay, and the different objectives can be possible for the optimal power flow, like either minimization of the cost, network losses, redispatch cost, adjustment cost, load curtailment, or maximization of the social welfare as well. So this I think we all aware of. And if you see in this particular problem, uh, let's say this particular problem has n number of generators. So can I distribute this particular problem in n sub problems? So I can say that PG1 is x1. Let's say n is 3. So PG1, PG2, and PG3, these are the three variables in this problem. Can I distribute this problem considering PG1 as a x Pg2 as a y, and Pg3 as a z.
No, sir. Because
Uh,
the
yeah, yes,
the power there is one equation where Pg1 plus Pg2 Pg3 should be less than or equal to this constant would be violated, no? Or this constant would
yes.
because
So it is a complicating constraint kind of coupling or complicating variable kind of coupling.
yes,
Which kind of coupling is there?
complicated complicating variable, right?
And no, it is complicating constant. That if I remove this third constant,
Yes. Then it can be
then yes, then we can solve Pg1, Pg2, Pg3 all separately. So the only coupling constant is the power balance constant, which is equation number 3. And is it correct? The equation 3?
equal something
Yes, either it should be equal or
greater than.
yes, thank you, greater than equal. So thank you for paying the attention. So this particular should not be less than, it should be either greater than or equals to. So this part, I don't have a pen here. Like, I don't know where it is. Comment. So this should be a equal to constant. Okay. So this particular constant is a complicating constant. Now, how can I get rid of this particular constant? So if you see, you know, if we look at our ELD problem, it is basically minimization of total cost, CI, PGI, subject to be very honest, we are not, okay, wait. I have to share the entire screen so that you can see. So it is basically your PGI is basically something PGI max and PGI min and summation of PGI equals to PD. So this is the constant we have. Now this particular constant is complicating constant. Okay, this particular constant is complicating constant. And how can I get rid of this? So what we can do is we can write down the Lagrangian function. We earlier also written this. So say, let's say summation of Ci Pgi plus certain lambda and Pd minus summation of Pgi. Okay, so this is the particular problem, and then what I can do is I can try to solve this particular problem where so this is the like minimization of this particular function and subject to PGI less than PGI max and PGI min. So this entire problem becomes like this, but still this part is here. Now there are multiple ways of relaxing this particular constant. So one way is like I can just assume that the only so total variables are like PG1, PG2, and PG3, and so this is a one variable set, and we are basically breaking it down into, let's say, PG1, PG2, and PG3. So three sets we are breaking it down. So if I have to solve this particular problem, I can write down certain uh, conditions, and that will be, let's say, with respect to PG1. So it is uh, ICI PGI del upon del PGI minus PGI lambda equals to 0. Okay, so this is the one constant with respect to only variable, let's say PGI variable. And if you look at this particular problem, this lambda is providing that coupling. If we look from the dual variable point of view, so this lambda is creating the problem. So our lambda iteration method is basically, you can say, a distributed kind of method where we one thing is, whenever we are writing down, decomposing these single problem into multiple problems, obviously in one iteration you will not get solution. So you will solve sub problems, then they will communicate the values, try to update this fixed value of p1 in case of complicating variable. In case of complicating constants, we can again divide that problem into multiple, three parts in this particular case. And then once it has been solved, so we will obtain some values of x, some values of y, and some values of z, and we will try to see whether this constant has been satisfied or not, this complicating constant. If it is not, then we will devise certain update rule, and that update rule will basically further change these three. Like we will further solve these three problems. Again, do some updates in the objective, and then we solve it in iteratively. So we'll get some solution iteration in iteratively. This lambda iteration method is same. We assume some lambda, okay, some initial lambda, and we solve separately. Like P1 is sold separately, P2 can be sold separately, and P2 can be sold separately. So these are basically three different solution approach sold at individual level. Once it has been sold, then we will again converge it to basically get a lambda update. So lambda will be updated. Then again we can solve it separately P1, separately P2, and separately P3. Okay, so and then further again we will do the update in the lambda. So this is how we can handle the complicating constant and solve each problem separately. So like generator 1 is not sharing any information, and it can be solved separately. Now if I come here, so economic load dispatch problem can be converted into DCOPF problem as well, and we have to add some power flow equation and equality constants, and then adding line flow limits as an inequality constants as well. So this is our DCOPF. We discussed it about it already. The assumptions also we have discussed, that no resistance or no losses are there, voltage magnitudes are constant and equals to 1 per unit, and the variation in the voltage bus angles is considered very small. So with those assumptions, we were able to obtain this particular objective function. Again, if I ask you in this particular function, which constants are complicating constants and which constants are not? Which equation number is complicating constraint?
Or is it number 6?
Yes, number 6 is power balance equation, and 7 as well.
Mhm.
Equation number 7 as well, because you know so first of all you have to look at the number of variables. What are the different number of variables? And based upon that, we have to basically decide like which constant will uh, are restricting the solution, okay, to be solved separately. So next, if I will, okay, we will discuss like how we can distribute these problems. So if we go for the ECOPF, we also consider both active and reactive power balance equation. Earlier it was only active power balance. Then losses are already like part of the formulation, so we don't do it. And they are non-linear in nature, very much complex to solve as compared to the linear version of the OPF. And generally we write it down generalized formulation is minimization of some fx subject to some equality constants. So those equality constants are real power balance and reactive power balance. and the inequality constraints are real power limit, reactive power limits, okay, generation limits basically. So real power generation limit, reactive power generation limit, voltage limits, and your power flow limits. So those are the uh, inequality constraints, and this is what the sum Lagrangian function. So first is why we are doing it, why we should solve it separately. So one very basic answer is, if the problem size is too much large, we can handle the entire problem into multiple parts, and we can solve this entire problem at a localized level. Another is like just so the conventional transmission system, it is okay that it is sold centralized level, but if we look at the optimal power flow in the distribution level, and if we are saying that no system operator is there, no distribution system operator is there, then those small clusters of the distribution sector, they should be able to optimize their objectives and still able to solve the entire problem. So they don't have that much large computational facility. So we can say that some agent based for operation can be performed, where each and every node is an agent, and they are all working together to get a social or global optimal point, or social like point where everyone is happy. So distribution of the centralized operation problem into different agents. So we can do it with the agent based operation. The very good question is, what should be the level of distribution? So, like in economic load dispatch problem, I have asked you that, okay, if I have to solve the distribute the problem with individual generator level. So PG1, I have created one different problem. PG2, it can be the different. PG3 can be the different problem. The earlier example was like some X variables was considered as one problem, Y variables were considered another, and Z was considered some another set of problems. So out of many number of variables, we can we distribute it to the individual variable level? Can we distribute it up to a group level, that okay, group of variables should be considered together? So those are again the question, like what should be the level of distribution? Okay, so one is in our optimal power flow kind of problem, or economic load dispatch kind of problem, we can say that it can be regional or node level distribution. So that is a question mark. Okay, you can have a distribution of, let's say, different regions. Let's say Rajasthan is solving its own problem, and Gujarat is solving its own problem. So different states are solving their own problem, and they are not and if I go with the node level distribution, so let's say for the transmission level, if there are few nodes in the Rajasthan, then we are composing or basically decomposing the entire problem to the individual node level. Okay, so that is again question mark, like how much distribution or what is the level of distribution at which you are looking at the problem. Okay, so this level of distribution, now can you tell me, let's say if I'm solving the entire problem altogether and I'm able to do it, that I have enough computational facility and the problem is not that much large, and we can solve it on a, like with decent computing facility, we can easily solve the entire problem. If I solve it, let's say divide that entire problem into two parts and solve it, so which one will take more time if problem is solvable with a decent computing facility?
The outer part of the problem, like inner part will be solved one time, but outer part will require, means if it is nested like the way,
Mm-hmm.
then the outer part of the problem will require the inner part of the problem to be solved. Then the outer part will be will will be computed.
Yeah,
So it
like
will take more time.
so we have to basically solve the individual sub problems. Then whatever is the complications, whether it is complicating variable or complicating constants, that will be solved. And then whatever is the outcome or like update because of that, like complications, complicating variable or constant solution, that will be again reflected back to the individual sub problems. Then they will update their own solution, and we have to do this iteration basically for a
Yes.
quite some time. So it takes time. Okay. But if problem is very large and the dimension of problem is too much high that we cannot solve it with the existing computing facility. Okay. In that case, if
Yes.
dimension is too much high, then solving on the, like with the distributed sub problem is easier because we can split the problem into two parts. One problem can be solved in one computation facility, another problem can be solved in another computation facility. They can communicate and solve over time. So one is we cannot solve it. Okay, a very large problem is there we cannot solve with our computing facility. And then let's say with our computer like my PC, let's say if large size of the network is there, lot of variables are there, my solver or whatever the the tool I'm using, that tool is not able to handle those scalability of the problem. Then I have to divide the problem and solve it on two different computers. Okay, so that is like so if I'm dividing a very large problem into two parts, it's basically regional distribution. Okay, and in terms of power system, if I talk about entire India can be divided into multiple regions, and then those regions can also be, it's not like like state wise region. We can have like earlier we had five regions, right? In the like north region, northern, eastern, western, southern, and northeast. So five different regions were there. So those kind of distribution can be provided with respect and they are coupled with the tie lines, or we can go up to like very end node level. So if you go like what is the degree of distribution or decomposing the existing problem, that will decide how much time it will take or whether it will converge or not. As sometimes it may not converge. Okay, so but what is the benefit of it? So we have talked that drawbacks are there, but what is the benefit? So sometimes that local knowledge of supply and demand profiles are available with a particular node. So in India, it's okay that we are one country, but if I look at the like Europe, there are different countries, and maybe they do not want to share their demand and supply profiles to a one aggregator or one system operator who's solving this problem. So what they will do is they will take care of their local uh, region, and they will communicate certain necessary information with the national level, or basically like the entire between different countries level, one to aggregator, and then they are solving the entire problem together. So local knowledge of supply and demand profiles are available, so we can assume that, and we do not want to share that information because of some privacy concerns. Okay, the knowledge of network, again it's basically like sharing a knowledge of entire network to some other country or one aggregator, where the from where the data can be pass on to some neighboring country or neighboring region. If we do not want to that, we can basically again go for the distributed kind of solution, that okay, I will handle my own grid, and we will only talk when there is a congestion, or basically like something needs to be done with the tie line, which is the connection between the two regions, and local knowledge of network is available. So in this, basically, we will have a communication with other agents, and each agent is responsible for one region. Okay, one region or one node. So it is again up to that what is the degree of distribution. So why distributed optimization? So it is basically agent-based formulation we can formulate. The agents don't want to share the information because of the privacy concern. So it is very much likely that we do not want to share the information. And each agent will have the knowledge of its local network. So If we talk about cross country point of view, both of these points are valid, that they don't want to share the cost coefficient or the cost information of their generators. They do not want to share the information of the network because of the privacy. Okay, and if we look at the very end of the distribution network, where no distribution system operator is there, and then we want to solve the problem, then we don't even know the network information. So each node can know the its neighbors information. So local network information is known, that okay, these are the lines, and by some means I'm able to identify the the information, that okay, I'm connected with two nodes only. So this is my area of scope, but I don't want to share my demand profile. Okay, so that is also like I don't want to share the information. So we can look at the problem at very small level as well, that the distributed optimization can be needed. And another example is like sometimes this um, transmission distribution coupling is there, and the solution of this kind of transmission level, we solve it differently, and for distribution level we solve it differently. So if we have to solve both TSO DSO coordination kind of problem, then distributed optimization can be helpful there as well. So for a OPF problem, we have defined certain variables. So let's say P and Q are active and reactive power generation. Generally, I call them control variables. And then we have some state variables as well, like voltages. So this E and F is basically real and imaginary component of the voltage. Okay. So, and some dual variables are also there, and we can write the entire problem like this. And there are some decomposition techniques which we will discuss about, like ADMM and OCD. But for the time being, let's assume this is the you know our one diagram. Now, how I can solve this particular problem? So let's say DCOPF, if I talk about, so let's say one generator, one load is here, one generator and one load is here, and I can divide this problem into area A, area B. Okay, and this line is basically the tie line, and this single node can represent a area as well. That entire area can be represented by this particular single node. Okay, and then this node is can be either, if it is two node system, then the distribution is at two node level. If we are assuming that it is not a node, it is a basically entire area, then we can call it a regional distribution as well. Okay, so this is how we can break the problem into two parts, and we just need to know, like this some information will be communicated on this side and some information will be communicated back, and we will able to solve the particular problem. Same can happen with the ACOPF as well. So ACOPF basically some P plus Q will be there, P plus Q demand will be there, some voltages are there, and reactive power and force. So this is kind of problem can be seen. Some control areas, let's say there are three control areas and they are connected with certain tie lines. Then we can solve the entire problem in, let's say, in three sub problems. So just to give you one easy example, I have used a rectangular formulation of the ACOPF, and let's discuss about ADMM first of all. Like, what is ADMM? Okay, so ADMM is alternating direction of method of multipliers. Okay, so let's say this is a two bus system, and we are trying to decompose the problem to the node level, and we have assumed a agent at ith node, where some variables are defined like ui, xi, and xj. Okay, so can you Roshan, that will be powered off the screen? So if I look at this particular problem, so let's say we are looking at the ACOPF, and we will see at the minimization of C1 P1 plus C2 P2. What will be the constraints? The constraints will be basically like the active power balance equation. So it is Pg1 minus Pd1 equals to P12, and this P12 is function of basically V1, V2, delta 1 and delta 2, right? This is so I'm just writing down for two bus system only. Okay, one generator is connected here, one load is connected here, another generator is here, and another load is here. So for two bus system, I can put that this is bus number 1, this is bus number 2, and the power will be P12 plus Q12 on this particular side, and this side will be same Q21 and P21. So this power formula is what? V1, V2, Y12 cos theta 12 minus delta 2 plus delta 1. Okay, so you can see that this is a function between V1, V2, delta 1 and delta 2. Other values are basically network information, which we are assuming that we know. So the problem can be written down like this: Pg1 minus Pd1 equals to a function of V1 and delta 1, V2 and delta 2. Similarly, you can get the similar expression for the Qd1 as well. It will also be the function of V1 delta 1 and V2 delta 2, some other function, okay, delta 1, F1 and F2. So this is one part. Then I can write down the power balance equation at node 2 as well. So let's say Pg2 minus Pd2 equals to some other function, and that will be V2 delta 2, V1 delta 1, and then Qg2 minus Qd2 equals to some function f4 and v2 delta 2, v1 delta 1. Then I have Pg1 limits, maximum and minimum, and I have Qg1 limits as well. So it is Qg1 max and Qg1 min, and I can have v1 limits, delta 1 limits. Okay, so these are the like some simple if I put basically divide the entire problem, then I can put that some constants Pg2 are also there. So Pg2 max, Pg2 min, similarly Qg2 and maximum minimum limits V2 and delta 2 as well. So these are basically the limits. Any doubts that okay, this will be our very combined, basically centralized OPF, I would say. So let's say pi 2 minus pi and Qg2 max and Qg2 min. Any doubts that this part I think we have discussed earlier as well, that this will be the OPF problem. Is there any condition left here? Any condition is left?
So can we consider technical minimums of generators?
Sorry?
Can we consider technical minimum levels of generators?
Yeah, we have considered, right?
Yes, yes.
Some minimum.
I'm sorry, I just oversaw it. Sorry.
Yeah, some minimum limit is considered. It can be considered zero as well. Okay, so it's up to so just to keep it generalized, I'm considering that some minimum limit is there on the generators. So ACOPF problem is only this, I think, or some other equations are there as well. Some powerful limits should also be there, right? There will be some power flow limits and some reference angle limit. Delta reference should be equals to 0. Apart from that, this is a ACOPF problem. Okay. Uh, right now, I'm not going into, like, let's say the inequality constraint that will be, like, easy to understand. So let's say this is our a centralized ACOPF problem. Which constraint is basically if I want to break down this particular entire network into two parts, where node 1 is acting as a agent 1, node 2 is acting as a agent 2. So if I break it down like this, that this is some sub problem 2, and this part is sub problem 1. Can I do it? Can I solve these two problems separately? Can you tell me which constraint is complicating here, or which variable is complicating? Sorry?
Non, no, there is no complicating constant.
So, okay.
So the branch
let-
flow of constraints will be complicating in this case.
yes. So I can say that these are basically complicating constraints because this particular R is the branch flows. These four are the branch flows, and they are basically binding it the problem basically. If, let's say, if I get rid of these four equations somehow, or let's say if I am able to fix this f1, f2, f3, f4 functions, if they have certain fixed value, then this entire problem can be solved, like, minimization of c1 p1. And if you look at on this particular side, it is only one index. So node 1, let's say the variables of node 1 only. So P1, PG1, PG2, PG1 and QG1 are the variable of the node 1. V1 and delta 1 is also the variable of node 1. So if somehow I can fix this F1, F2, F3, F4, then it is basically easily solvable. So this power balance constraints are basically your complicating constraints here. So how we can handle this particular problem? So the generalized way, we can write it down like that. Say minimization of some certain function x1 and x2, okay, and subject to some equality constraints, let's say h1, which depends upon x1 and x2 equals to 0, and some another equality constraint which is x1 and x2 equals to 0. And so if you look at this above problem, this is x1 is nothing but pg1, qg1, v1 and delta 1, that these are the variables of node 1. I can say that the variables of node 2 are pg2, qg2, v2 and delta 2. These are the only variables in the above problem. And if I split the variables in this above centralized problem, I can say that x1 is pg1, qg1, v1, delta 1, and x2 is pg2, pg2, and v2, delta 2. So we can split the variables. The above function is also can be easily distributed, that some cost function in x1 is there and some cost function into x2 is also there. So I can say that this entire problem can be distributed. This H1 is what? Power balance equations. Power balance equations at node 1. So these are the power balance equation at node 1. These are same power balance equation at equations at node 2. Then rest of the constants are basically these. So if these two are basically power balance, so this is nothing but the power balance constants. Power balance equations are these. If you look at this particular part, I can say this is nothing but creating some solution space. So I can say that some x1 is basically defined by some constant or x. So this entire part is defined like this. Okay, and then similarly I can define that sum is basically defined like this. So the entire above formulation centralized OPF problem can be defined like this as well. It is still the same single problem. Can I distribute it now? So if you look at this one, that I cannot decompose this particular constant. So these power balance equations are basically coupling the problem. Otherwise we can easily solve this particular problem. So even this function is also like c1 x1 plus c2 x2, right? So like the coefficient with respect to in x1 q v and delta are 0, and here again q v and delta coefficients are 0, and pg1 pg2 coefficients are as per c1 and c2. So is this part okay? If you have any doubts, we can move that how we can distribute this particular problem. Is this fine? So let's say let's write down the Lagrangian function. So some Lagrangian function will be written down, and that will be uh, this function f x1 comma x2 plus, let's say, some lambda 1 h1 x1 comma x2 plus lambda 2 h2 x1 comma x2. Is this clear? Subject to x1 is set of capital X1 and x2 is set of capital X2, and these sets are basically nothing but the limits on the variables which we have defined here. Okay, so these are nothing but the limits. If this problem is there, and if I assume that there are certain things which are constant, so this problem can be decomposed easily by assuming certain variables. So let's say it is basically minimization of f1 x1 plus uh, lambda 1 and h1 x1 x2, and where x2 part I have basically used as a constant term, that this x2 is constant. Okay, similarly another is minimization of f2 x2 plus lambda 2 h2 x1 x2, and x1 is kept constant, subject to x1 is set of capital X1 and subject to x2 is set of capital X2. This is how we can distribute the entire problem. Any doubt here? Can I distribute it like this? Anyone? So what we have assumed is here is uh, to solve the subproblem 1, we assume that whatever is the x2 values, if we fix those values, then this problem can be solved only purely in the x1 itself. Okay, if x1 can be constant, then this problem can be solved purely in x2. Okay, and we can solve them separately. So what we have to do is, so what we have did so far is we had a block. Okay, and then we had a objective function on top. The objective function was f1 x1, f2 x2. Some constraints was there which was defined by, like, all of those limits, some x1. Then we had some constraints on c2 x2, individual constraints. Then we had some h1 x1 x2 constraint and some h2 x1 x2 constraints. Okay, so these constraints were basically, the problem was like this initially, that you can split the objectives in x1 x2, you can split the conditions on x1 x2, but this h1 and h2 are power balance equations, are basically the conditions which are coupling them together. So these are basically the coupling constraints. The above method which we have discussed is called optimal condition decomposition, OCD. Okay, and in OCD what we are doing is we are again having a function f1 x1. So it's basically, let me build some blocks, plus some lambda, some h x1 x2 where x2 is constant, then some c1 x1. So this is one part, and then another is we have h1 x1 and x2 bar. So this will become h2 and lambda 2. Okay, similarly we can break it down into two parts again, that it is f2 x2 plus lambda 1 h1 x1 x2 where x1 is fixed, and then we have certain c2 x2. Okay, and then we have some h2 x1 x2 equals to 0, or equals to 0 as well, like whatever. Then x1 is constant. If you write down the KKT of these individual objective function, you will end up with the writing down the KKT of this part of itself, because um, here while solving with the x1 only, this constant I kept as a equality constants h1 x1, and this part I kept in the objective function. While solving with for f2, so instead of doing decomposition like this, what we did is, if I solved like this, then I have to use the x1 and x2 update. But instead of that, in optimal decomposition, what we do is we keep certain variable constant. There are two conditions, then we will keep one condition as a part of objective and another condition as a part of constraint. So the individual constraints will be kept as a part of constraint, and the some other sub problems constraint will be kept as a part of objective. So this H2 is basically constraint of second sub problem. So this is basically used here in the objective. Okay, and this is here as used as a objective here as well. Okay, now what is the significance of this? Like, what is the significance of optimal decomposition part? So if you look at the particular problem, okay, let's say I have a two bus system problem. I have certain generator, certain load, certain generator here, and certain load here. Now, can you tell me if I write? So, okay, we have written down these equations like power balance equation. What is the dual variable of this active power balance equation? What it signifies? We have discussed that part earlier. ये जो एक्टिव पावर बैलेंस इक्वेशन है इसका ड्यूअल वेरिएबल का मतलब क्या होता है? What it signifies? Anyone who would like to answer? So we have solved it mathematically. Now try to visualize from the power system point of view. So what is the meaning of this particular constraints, like the dual variable of this constraint? Power balance equation.
Increase in injection with respect to unit change in
It
F1.
is the sorry, it is the
Increase in power injection with
hmm,
respect to unit change in F1 or the voltage.
right, or we can say that that is LMP as well.
Yes, sir.
Right, we established that part earlier when we were doing OPF, that the dual variable of the power balance equation with the cost minimization objective represents the locational marginal price. Okay, so these are nothing but the shadow price of active power and shadow price of reactive power, you can say. So if some lambda is here, so let's say some lambda 1 and lambda 1 p, and let's say this is lambda 1 q, and same we will have some lambda 2 p and some lambda 2 q. Okay, so some lambdas are there for these with respect to these power balance equation, and we can say these are the shadow price of active power and reactive power at different nodes. So it is like for active power, multiplier is also called locational marginal price. So just keep that in mind, that we have some lambda 1 here and some lambda 2 here, and I'm just now talking from the active power point of view for the time being. I'm not talking from the reactive power point of view, and we will extend the same philosophy further. So we have the variables here, like this pg1 plus j, qg1, pd1 plus j, qd1, and some power is flowing, which is p12 plus j, q12. Let's say if I have break this particular network into two parts, and if I just don't look at the other side, can I write down the power the objective function here? It is minimization of c1 pg1 subject to power balance at this particular node. So that will be pg1 minus pd1 equals to p12. Is there any doubts in this particular part? If I am just looking at the node 1, I can write it down like this, and similarly qg1 minus qd1 equals to q12, and then pg1. Roshan, am I audible? Some network
Yes,
issue
sir.
is shown. Okay, yeah, thank you. So maximum limit and some minimum limit are there. and these are basically based upon the voltages. So those voltage will also have certain limits. Is this fine?
Yes, sir. Yes, sir.
Right. Now, just visualize one thing. Let's say power is being supplied. If power is basically 1 to 2, then this P12 will be positive. If this P12 is positive, it means we are supplying the power to the node number 2, right? So we are supplying the power to the node number 2, and what will be the price of node number 2? That will be lambda 2, right? If you are supplying power to the node number 2, and the price of node number 2 is lambda 2, how much money we will get as a node number 1? That will be multiplied with lambda 2. So I can say that I'm minimizing the cost. Then I can basically put it like this, that I am maximizing the lambda 2 and P12, right? That this is the money I will make if I supply this P12, and this is the cost I am minimizing to produce certain power here, which will flow in this direction, this direction. Okay, but the issue here is in ACOPF problem, if it is DC, that is perfectly fine. But in ACOPF problem, some losses will be there in between, and whatever is the power here, like the direction P12, and in this direction it is P21. The power here will be something different, and the settlement will be the power which is on node 2. So instead of using this particular part, we will not use this one. We will say C1 PG1, and instead of minus, I will say lambda 2 and P21. I will just reverse the power flows, and it implies that to satisfy this particular load, which is this one, some power is coming from some generator G1. So that is the cost we are facing. Okay, and some power is coming from the node number 2, and some lambda 2 we have to pay for this particular power P21. So this is the overall cost to supply the uh, P12, or basically PD1, the demand of PD1. So this is basically we are paying for. So we can write it down like this, that this is the minimization of the cost, and some LMP based money will be paid to the generator 2 to supply this one. And if it is active power, I will put lambda 2Q, and I can also put lambda 2Q 2Q 21. And then if I have written down like this, I can solve it separately. And this is what we have mentioned here, that it is F1, which is the cost at the self node, lambda 2 is the LMP of the second node, and H2 are basically the power coming from 2 to 1. Okay, and then these are the limits, and H1 is basically power going from 1 to 2, because here these P and Q with respect to the variable terms, and if you look at the power flow point of view, it will be 0, because this in H2 equation, H2 has both Pg2, PD2, and power flow. This nothing but this F3 is power flow, and but we have also assumed that all the x values are constant. X2 values, like the values of the neighbor are basically the other node, are kept constant. If they are kept constant in this particular part, Pg2 will be constant. If Pg2 is constant, then it like putting that into the objective function will result in a constant function. So the only variable is f3, and f3 is nothing but the power flow. So I can simply write it down like this, that these lambda here, like this H2, which is equality constant, but it results in the only power flow. Note the Pg2 will also be there, but that will go in the constant part because we are considering x2 as a constant. Are you able to comprehend what I have discussed, or whatever we have discussed so far, like how we are doing it? Anyone? If you have any doubts, we can discuss. Otherwise, I will proceed the next part of this algorithm, or optimal condition decomposition. So this is the significance I am talking about, that this is how we can decompose the problem by keeping x2 constant here. Then the only x1 variable is here, and we can solve the problem in distributed way. So what we can do is we can solve the particular problem. It's like a minimization of f1 x1 plus lambda 2 h2 x1 x2, and x2 is constant. So if it is constant, we don't have to worry. The only issue is still the problem. Then our x1 is set of capital X1, so all the limits are there. And then h1 x1 and x2 is constant, and that is our equality constant. So we will solve this particular problem separately. Then another sub-problem in terms of 2 can be written down similarly. And what we will do is we will initialize certain lambda 2, x1 and x2 initially. Okay, we will use those values first of all. Then the outcome of this first problem is what? You will get some x1 new value and the dual variable of this one as well. So lambda 1 new value. Or let's not go into there. We can use the update rule. So x1 new value will be there. Similarly, this problem will have f2 x2 plus lambda 1 h1 x1 x2, where x1 is constant subject to x2 is set of capital X2, and h2 x1 x2 equals to 0, where x1 is constant. The output of this will be x2 star. These x2 and x1 and x2 star can be used to update the lambda. So the lambda 1 k plus 1 will be lambda 1 k plus certain alpha h1 x1 x2, the optimal values. Similarly, the lambda 2k plus 1 will be lambda 2k plus alpha and h2 x1 x2 complicate optimal values. So these are like optimal values. Okay, so this is how we can update the lambda. Once lambda has been updated and x1 and x2 have also been updated, so now instead of this existing x2, we will use the new optimal value of x2, whatever is the new optimal value, and we can keep on solving this particular problem until the convergence happens. So this is one way of solving the problem. Is there any doubts? Okay, so this is optimal. Another is ADMM. Let's discuss that as well, like how ADMM works. So ADMM is generalized way I can write down that, let's say some f1 decomposable objective function is there. Okay, f2 x2, and subject to that x1 is basically part of capital X1 and some x2 is part of capital X2. Okay, and here what we can do is, like, we can say that sum of x1 are equals to x. So this is the generalized statement of ADMM. Here we can write down some Lagrangian function and generally augmented Lagrangian, and that is basically like f1 x1 plus f2 x2 plus some lambda, and then a x1 minus x2 plus, so this term gives you the direction. Some another square term or norm term is basically taken, that the penalties should be always positive, uh, the second order norm. So this is the augmented function. This term is called augmentation, and here we will solve x1 t plus 1 equals to minimization over x1 set of capital X1, and whatever is this our Lagrangian function with respect to x1 variable, x2 variable, and we will keep it at some t, or let's say k. Let me use k as a iteration. So k plus 1 will be this, and some lambda at the k position. Then I will solve for the x2 variable, and that will be minimization of x2 set of x2 and Lagrangian function. This x1 we will use k plus 1 now, whatever is the updated value, and we will assume that x2 is the variable and lambda is basically our k, and then we will update the lambda k plus 1 equals to lambda k plus certain alpha. Generally we keep it value equals to c, and then a x1 minus x2. So this is how we solve it, we solve it this, then solve it this, and then again solve it x1. So these are the different steps, okay, by which we can solve a particular problem in ADM. Now, for a two-bus system, you can say or question that how the entire problem should be kept, or how we can formulate this kind of formulation for the two-bus system. So, if I look at the example, I will use the same minimization of C1 P1 plus C2 P2, and subject to P1 minus PD1 equals to, uh, we have V1 V2 y12 cos theta 12 minus delta 2 plus delta 1. Okay, as you can repeat that for the reactive power as well. So then P2 minus PD2 equals to V2 V1 y12 cos theta 12 minus delta 1 plus delta 2, and similar for two, and limits will be placed. Okay, whatever the limits. Okay, so those are we know that they can be individualistic. Now, how to define this particular problem, or if I want to solve this particular problem with the ADMM, what I will do is I will first of all define x1 and x2, because I need some x1 and x2 and solve it iteratively, and I have to define that. Then if I define some x1 and x2, the entire constraints are basically the solution space is defined in x1 only, and sum of x1 are equals to x2. So if I define in this particular problem that x1 is p1 q1 v1 delta 1 v2 and delta 2, and x2 is basically p2 q2 v2 delta 2 v1 and delta 1. This v2 is copied both the positions, so I can say that the objective part can be divided into c1 p1, which is in terms of x1. Okay, so this part can be converted, that this is as objective function, then subject to we have these constants. Okay, if you look at that, this constant is complicating if I'm dividing the entire network into like splitting that part from the middle. Then P1, V1, V2, and delta 1, delta 2 all are defined as a x1 here as well. So I can say that the first constant, which was the power balance H1, it is actually in x1 itself only. This particular constant is actually in x1 itself if I have defined V2 and delta 2 as well in the x1. Similarly, we can do it here as well, like minimization of C2, P2. So this can be converted like some function in x1. This can be written down some function in x2, and subject to it is what, h2 and purely x2. Okay, so this can be converted. Earlier it was like h1 and x1, and this is nothing but the h2 and x2 if x1 and x2 are defined in such a way. Okay, once this has been identified, we can similarly we can write down for q and then limits. Similar is for q and limits. You can see we can easily distribute it, but one part is that this at the optimal point, this voltage should be equals to this voltage, and this V2 voltage should be equals to this particular V2 voltage. So I have defined it like this, some matrix A is there, some x1 is there. Okay, so we have defined it like this, sum of A x1 is equals to x2. So is equals to x2. So x1 was P1, Q1, V1, delta 1, V2 and delta 2, P2, Q2, V2, delta 2, V1 and delta 1. So the first row will be 2, 3, 4, 5 and 6. So first row will be 0. That it is perfectly fine, and we are multiplying it with the 0. Okay, or we don't even need, I think, first row. Yeah. So if I put, then the P2 will become 0. So what I will do is I will discard these two rows. Then if I have to write down only in terms of V1 and delta 1, which are basically the coupling variables. So I can say that V1 0, delta 2 is 0, 1 and 0. So this entire part will be removed, then this size will also reduce. Okay, and then delta 1 is basically 0, 0, 0, 1, and this is basically 1, 0, 0, 0, 0, 1, 0, 0. Okay, so this is how we can put it, like sum of A x1 equals to x2, and it is nothing but it is saying that V1 should be equals to V1, delta 1 should be equals to delta 1, V2 should be equals to V2, and delta 2 should be equals to delta 2. So these are the, and coupling. So basically we are what we have done is we created a copy of voltage 2s in the x1, and we created a copy of voltage 1 in x2 as well. So we just have to like we can solve the entire problem or sub problem separately, and we just have to update that okay, these copies should be equal at the optimal point. So the ADMM works like this, that the entire problem can be separated out in with one constant, and then few of the variables are equals to the other variables, and those conditions can be placed as a penalty terms in the function. So these are like augmented Lagrangian function we have where we have placed as a penalty, and then we can solve it iteratively. So this is like first step, okay, then second step, and then this is our third movement, which is here. Is there any doubt how we can use ADMM? Ankit?
Sir, I have one question, sir. Sir, we have divided one main problem into sub problems.
Yes.
So, so the procedure is similar for dynamic programming, or this
Yes,
process?
yes, we can. Very good question. Uh, the procedure there will be different. The thing is, here the time complexity or the variables were not, coupled over the time. In dynamic programming, the variables are coupled over time. So if you want to, distribute with respect to time, then I can define. Okay, in dynamic programming, if I have to do, I can create two copies. Yes. So let's say if you want to decompose in terms of time couplings are there in the variables, which is like unit commitment problem or any dynamic programming. So basically, what happens there is some variables are timely coupled. So we can create that two set of all the variables. The two sets of all the variables, solve one set separately, solve another set very differently, and then only the time dependencies can be placed as a ax1 equals to x2, like this particular constraint. The time dependency, I can share a good reference paper with you about this one.
Okay, sir.
Okay.
Thank you, sir. Thank you.
Yeah, for like how we can distribute the centralized problem if time coupling is there. That is the core of the genetic sorry, this dynamic
Dynamic
programming.
program.
Yes.
Please
Yeah, i
upload
will
it.
i will
Thank
yeah,
you,
i
sir.
will i will upload that in canvas.
Canvas.
Roshan, check for one of my paper written with Abhishek. Okay, and please upload that one. So you can, I think, go to my profile. There is one paper, and I will okay, don't worry about it. I will upload that on the uh, canvas, that my paper as well, and like we took some reference, so we will upload that as well either. So yes, yes, if you have any doubts further. So this part, I think we discussed that. Okay, like the problem is this: we can keep certain copies, like the voltages E2, F2 are also kept here as a copy. The E1, F1 are kept here as a copy, and then we were able to formulate something like this. In this particular part, these multipliers should be zero actually. Otherwise, if I use exactly the same this table, then it says that pg2 equals to 0, which is not true. This says that pg2 equals to 0, which is not true. So yes, so this is x1 and x2, and generally um okay, here I have defined generally in generalized way that if we are distributing to, let's say, at each area level or node level, the copies we will keep only for the state variables, which are voltages, and note the control variables, which are our power generation. Okay, so U is defined as a power generation, active and reactive. X1 is basically your voltage variables. Yes. Okay. Oh, it's okay. I will share that with you, so you can upload it. So, and this is basically ADMM formulation. Okay, yeah, this is the OCD formulation which we discussed. So yes, we are about to end our session, and there is a question: is there any other electricity or energy related talks to be held in future by E&ICT team? So, to be very honest, in next financial year, we will repeat these two courses. So, whoever like maybe if I'm have some updated syllabus, I will put it on my LinkedIn. And if syllabus is something else as compared to what we have covered so far, then you can join. Otherwise, I will not recommend, because to create the entire course it take a lot of time, and we would like to run the same course multiple times for the different set of participants. Yeah, but some other talk if I consider, so one purely on the market has been proposed. We don't know, once it is approved for the next financial year, it will be floated. And I'm planning to propose a pure decomposition based course as well. But I don't know, many of you are will not be interested, because it will be purely mathematics, and that is purely on decomposition part. So maybe if if it is approved, I will float a course purely on the what different decomposition techniques and pure optimization. And apart from that, I think I have also planning to propose a pure cybersecurity course as well. But let's see whether we will able to do so. So once the courses has been approved, it will be placed on the ICT Academy, and I think you are like placed in some mailing list from the ICT Academy, like as you are the participant of this one. So the future course information will be emailed to you, whether maybe they are relevant to you, or maybe they are sometimes not even relevant. But the information are always forwarded, like whenever some new program is going on, is sent to all the participants who have basically like the earlier previous participants, like all the alumni of the E&ICT courses. So that information will be shared. So depending upon that, looking at the brochure, you can look at the syllabus. If you feel that that is helpful, you can definitely join. Okay. So this part, I think we have discussed already, like OCD formulation, that this was a centralized formulation. Then we can debug this one and then update the lambdas. Yeah, thank you. And yeah, this we have discussed. Now let me tell you. Okay, so far we have discussed theoretical parts. One interesting part is missing. Let me discuss that with you. So I tried to solve distributed optimization for OPF with the help of OCD, and whatever we have discussed so far, like the same fundamental problem. So this is you can see it on your screen as well. So this is the fundamental problem which we tried to solve. It was not converging. Let me tell you, it was not converging, and why that was not happening, I will give you that answer as well. So what happens basically, like when we are writing down these constants, if you are solving it to certain regional level, then it is perfectly fine. But let's say I try to solve it for a distribution network. Okay, and let's say certain nodes are going from there. Sorry. Now let's assume there is a load here and no generation. So if I wanted to, distribute it to the node level, let's say this is third number node, so it should be minimization of C3 P3. Okay, and as there is no generation, so this term will be 0, plus let's say this is node number 2, 4 and 5. So I will put some lambda 2 and P21 plus lambda 4 P43, sorry, 23, and plus lambda 5 and P52. And to be this P23 is not one variable, it is basically like, we use that V2 V3 Y 23 and cosine of theta 2 and minus delta 2 plus delta 3. So that entire power flow term is basically placed here. It's not simply single variable. Subject to we have this P3 minus PD3 equals to P, sorry, 32 plus P34 plus P35. Okay, again this is 0 because we don't have any generation here. Now because of the these lambdas, they will converge in later on stage, but initially we will start with certain fixed value. Okay, and then what happens that these power flows is P23, P43, P53, which are almost equal to, or almost going to be equal to these values, they become 0. If they become 0, this demand cannot be supplied. And because of this particular hard constraint, because here, like whatever is the variable here, x4 here, and x5 here, in OCD, we assume them constant. If all of these variables are constant, and by mean variable, basically these are voltages which we are making constant. So if these voltage at bus 2, bus 4 and bus 5 are constant, how much power can flow between like tightly coupled node and where all the variables are constant, and so the power flow between this 2 to 3 and 4 to 3 and 5 to 3 will be very minimum. And if this demand is too much high, PD3, then these power flows will not be able to cater this demand and it becomes infeasible. This becomes infeasible. So to handle that one, we modified this one OCD problem, and we solved that. Okay, all the voltages will be updated in some particular sequence, and we will only solve the control variables. So we assume that so in the conventional one, we kept fix the neighboring voltages, like whatever is the like self voltage, that will be kept as a variable, and other neighbors information will be kept as a constant. But here what we did is we neighboring voltages are like relaxed, they are kept variable. So instead of keeping them constant, we let them allowed to be vary the value. So the voltages are basically keep on varying, so that we have that flexibility, that if these voltages are not fixed, then the power flow can be realized to supply a very high demand. If certain demand is very high, so then these power flows will uh, take some values, and in such a way that they can cater this particular demand. Okay, so we allowed them to be relaxed instead of constant, then solved the control variables. Then, so like, for each node, we only solved for the power generation. That's it, nothing else. We solved it for the control variable, which is power generations only, and we forgot about the voltages. Once we solve a particular node, we do not care that what was the voltage value. Then, so in a radial network, we started from the end node, like 4 and 5. In backward direction, we solved the power generation values. And once we reach to the bus number 1, which is our reference bus, and its angle is 1 angle 0. So once 1 angle 0 has been identified, and we know that some power generations has been there, based upon that power generation and whatever is the previous voltage value, we were able to calculate the current, and the total current can be calculated in each branch. Once in each branch the voltage currents has been calculated, we can calculate the, so branch currents can be calculated. Then from branch currents, voltage drops can be calculated. And if voltage drop can be calculated, I can calculate the voltage at uh, child nodes. So this was the one relaxation I did. So this kind of formulation basically gave me the solution. But if again, this will also fail if voltage limits are very much tight. So this was some algorithm which we used. In backward sequence, basically we received the dual multipliers and solved the OCD formulation which we discussed, and only obtained the power generations. In forward, we calculated all the currents and branch currents, and respectively we were able to calculate the voltages of the each child branch. We use this particular one, and this is the convergence diagram, that the tolerance is basically converging in 50, almost 50 iterations. It is very low, but if you see, like, even after the 50, it is still exponentially decreasing. So the algorithm was working very fast, and we are getting very good results. Like power generations, at the different nodes were settled after the iteration number 50, and voltages are, there are some fluctuations, but they are in range of 10 to power minus 5. Okay, so that is like acceptable, and some time is also here. So this is it. If you have any doubts, you can ask. Quiz syllabus will be second week only. Whatever the topics we have covered in after quiz 1, so Monday to today, that will be the part of the quiz. It will be tomorrow, available I think after 9. So 9 onwards, 9 a.m. onwards, it will be available, and you will still have 30 minutes to complete the quiz. So you can attempt the quiz at any time as per your convenience. So if you have any further doubts, like, so today is our last day, you can email me. You can email the other expert as well, like Professor Bakar was with us, Professor Prerna Jain was there, and Dr. Deep Kiran. So you can also email them and you can ask your questions. They will be really happy to help you out. Yeah. Thank you very much.
Sir, I had a request for you.
Yes.
We are someone who is working in a state utility in Gujarat for capacity expansion in the state of Gujarat, sir. So we are deeply linked with whatever you have taught us during last 2 weeks. But unfortunately, due to professional obligations, we were not able to follow through all of your lectures at the given time because of
Mm-hmm.
our indulgences elsewhere professionally. So
Yes.
I just request that you please extend the quiz deadline by about 1 or 2 days. So by the time by this weekend, we'll be able to follow through all your lectures and then be able to complete it.
So I think what we will do is um, you know okay, so instead of Sunday we can have the quiz maybe on Tuesday, then it is fine. So you can go through the all the videos. We will share the link on the WhatsApp group, and then you can attempt the quiz. So on Tuesday I can
Sure,
make it alive there. Okay.
sure, sir.
Thank you.
uh, yes, we will share a feedback link. Sir, can I con? Yes, Nishant, please, you can always contact me. That's completely fine. You can reach out to me on my email, or you can text me as well. and some modification or some formulation part I can help you. Whatever is your assumption, how to handle those assumptions, maybe I'm able to help you. Yeah.
Sir, till when these videos be available to us on YouTube? Is there any time limit, or we can refer to these videos later as well? Like,
So to be very honest, I think it is only to the storage limitations. If storage, if the new courses are keep on coming, so I think there is some certain storage limitations. If that storage is filled, then they will remove the previous old videos. Otherwise, it will be available on YouTube.
thank you, sir. Yeah.
Yeah. Yes.
So, as we come to the end of our faculty development program, we'd like to thank E&ICT Academy for giving us the permission. Also to Malviya National Institute of Technology, Jaipur, for hosting this event, and for the speakers who have contributed to this program, Dr. Deep Kiran and Professor Prerna Jain. I also thank the participants for actively participating in this program, and we hope to have your inputs in the quiz, and thereafter if you have any doubts, feel free to drop us emails and reach out to us, or if you wish, you can come down to the campus at any point of time and for any discussions with prior appointment. We as an institute take pride in supporting and developing domains in power and energy sector, and optimization in this sector is something that comes natural to us. Over the last 3 decades we have been working in this, and we hope to see more synergy in the industry in this domain. As industry structure is evolving, I think there would be many opportunities to learn new things. We'll continue organizing such events for the benefit of the participants, and we hope that there would be more interactions in this segment as well as other segments as and when possible. With this, I'd like to thank you all. Thank you once again. Thank you.
Yeah, if you have any feedback, you can provide that here. Though we will share the link feedback form with you, but if you
Yeah.
want to share verbal feedback, you can suggestions, anything you want to share, you can share that with us.
Thank you, sir, for hosting these sessions on optimization and its specific applications to the power sector. So from my side, I can say that this is a very new area to me, and this would certainly prove to be very helpful to help me get started into this area. And uh, personally, I think you went into greater depths, means great details to help us understand the nitty-gritties of optimization, and taking up different algorithms and explaining them in details. So thank you. Uh,
Thank you, Gaurav.
yeah, I hope we'll be able to reach out to you in future as well when
Yes,
face
definitely.
any
If you are
problem.
coming to Jaipur, you can visit us in the campus, and we can discuss personally as well.
Yeah, sure. Maybe primary mode of communication would be emails, but
Yes,
s-
definitely.
sure, we'll reach out, means we'll be looking forward for help in case we need some guidance in future.
Sure, 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 sure.
Thank you, Dr. Satish. Thank you, Bhagar sir.
Thank you. Any other input, feedback, we'll be happy to take.
Sir, I'll just take a minute at this point. In light of recent regulations by CEA, how resource adequacy is becoming more important for each state utility right now. We were working in this field of optimization and generation expansion since last 2 years. We were just trying to understand the process of optimization through results, not through the theory, because frankly speaking, it has been a very long period for us since we last studied any theory related to anything technical. So it was really a boon for us to be able to understand quite in depth and in detail how these models are really trying to communicate with us in terms of whatever values they throw at us. So feasibility for us was only to try and change the constraints, and whatever comes out to be feasible constraint was the output for us. So this, I believe, will give us better clarity going ahead, sir. Thank you so much for synthesizing this complete course for us.
Thank you.
So the sessions were very nice and very interactive, sir. And we learned many things, many good things. And Satish sir is explaining very well in all the aspects. Thank you very much, sir. Sir, if this program is again you again do, so sir, please sir, explain some other meta-heuristic algorithms also, like GWO and something else, which are useful in recent papers in battery management system or EVs.
Yeah, I will definitely try to include the latest algorithms, and I will also keep a few examples, like how we can use the like the latest algorithms to solve the system related problems or the new advanced problems as well. I will definitely try to keep them.
Thank you, sir. Thank you very much, sir.
Thank you. If you can turn on your videos, just like for a quick snapshot. Yeah, thank you. Roshan, are you able to take the sorry?
Share पर नहीं screen share
No,
नहीं.
change the layout. So
Subrat, Virendra, Sathi Narayan, Ankit, Ravindra Babu. Requesting all, please, if you can switch on your video for a quick click. It'll just take us a moment and we'll process it. And smiling faces as well. Lakshmidhar, Ravindra, Ankit, Sathinaran, Subrat, Virendra.
yeah, okay.
I think so. Whatever best is possible, we have taken it. Thanks for joining in. Thank you very much.
Thank you.
Thank you, sir.
Thank you.
Thank you. Thank you.